we have 2 hours today to really drill down into module specification sheets, inverter specification sheets, and understand the nuances of selecting the right material for the job. Now, solar is very scalable, and a lot of the lessons learned in residential also apply to commercial as well. And we have a live audience today, so feel free to ask questions, whether you prefer using the chat widget or unmuting your microphone and just talking to ask your question. Either one works for me. So with that, we only have 2 hours today. So generally, we're going to be reviewing modules, inverters, racking, learning more about the terminology and the really with an emphasis on specification sheets. And then hopefully what that's going to do is have us better understand some of the balance of system material. And we'll also talk about supply chain while we're at it. Where do you go to buy this stuff? So this will be much more of a material focused class. We're going to kind of stay away from too much design work, and we have other classes with PDH Pro, such as Design Your Solar Roof, that cover that territory. And so why do we want to do this? Particularly as building engineers, we have the decision-making capabilities, and if we can master solar design, then we can incorporate stunning projects that really aren't out of line with industry costs. And so if you happen to be in an area where the price of electricity or the solar policies are such to make it cost effective, we can start leading these projects and transitioning all of our projects into on-site clean power generation, and not let the contractor or some third-party service kind of drive the project. The more input as the building project lead, the better the result of the project. So let's learn a little bit about solar power. One of the main things is the industry calls them solar modules rather than panels. They're synonymous, but the technically correct way is to say solar module. The colloquial way is solar panel. I'll use them interchangeably in this program, but if you are filling out applications, if you're concerned about why are people calling them solar modules, solar modules is the industry way to refer to it, the code way. Panels used for other terms in National Electric Code. One of the main differences between, say, a utility scale panel and a residential solar panel is that most, not all, but most residential solar panels are 60 cell, and most utility scale panels are 72 cell. Now, there are some nuances, but what do we mean by that? Well, we're literally talking about the individual cell on the solar panel itself. So here we got 1, 2, 3, 4, 5, 6. And then if we counted all of these, we would get 12, and that's 6 times 12. That's a 72 cell solar panel. This is a different kind of solar panel. It has a black back sheet instead of a white back sheet. But if we actually, with a trained eye, kind of caught these cells, we would still have 6 cells across, but this module is just a little bit shorter than the utility scale one. There's only 10 cells down. That makes a 60 cell module. And literally the largest difference between these two different 60 cell versus 72 cell is the extra 2 rows of cells that give the 72 cell panel a little bit more height and a little bit more weight. It becomes a larger panel. And with utility scale projects, that larger panel means you get a slightly more bang for your buck all the way throughout the whole project. But the problem with these 72 cell panels is they're a little bit too tall and a little bit too heavy for one person to safely handle on a rooftop. And so generally for rooftop solar, you're dealing, especially residential slanted type rooftops, you're dealing with these smaller 60 cell panels. And then when you get into residential or commercial ground mounts, maybe residential ground mounts, you can use 72 cell panels on a residential rooftop. So if the rooftop is particularly easy, or you're a particularly ambitious installer already, there's no problem with that. It's just harder to manage, a little bit less safe. And rooftop safety, slanted rooftop safety is very important. Anyway, all that. What this means is, I'll just say a solar panel is about 3 1/3 feet by 5 1/3 feet. Just generally speaking, 3 1/3, 5 1/3. It's easy to remember, but actually, utility scale panels are a little bit taller, so they get to be, sometimes over 6 feet tall. And when I say a solar panel weighs 40 pounds, the utility scale 72 cell panel has 20% more cells, and it weighs about 50 pounds instead of 40 pounds. So a typical solar panel, I would say, is 3 1/3 feet wide by 5 1/3 feet tall. It weighs about 40 pounds, but the utility scale panels are a little bit taller, a little bit larger, but really not much different than the residential type panels. In a way, the solar industry is dumb silicon. We've had smart silicon and computer chips to do new and amazing things. Solar panels, just a bunch of concentrated silicon, pure silicon that happens to be photovoltaic, and so you can happen to make a solar panel out of it, but it's just kind of a dumb, heavy piece of material. Manufacturers know that solar goes outside. So the panels are designed to go outside. The manufacturers have hail test ratings. About 1-inch hail at 50 miles an hour will bounce right off a solar panel. That doesn't mean the solar panels are bulletproof, but in my experience, the solar panel is so durable and strong that it actually gives a false sense of security and durability. So it's like a nice piece of, it's a nice quality object. You can throw it in your truck and drive it down the road. It's not going to break or shatter. You can drop a solar panel. Usually you'll be okay. Sometimes a solar panel can fall, flat on its face, and if it it falls onto its own frame, it won't shatter or break. It's a durable object. It's designed to go outside, 1-inch hail. It's better than your normal roofing material in terms of durability. Long time warranty. We're going to get into that in a minute. We'll also get into some downsides too. But just general issues. And as far as which solar panel is best or to use, the market for quite some time has been a silicon market. And this is monocrystalline silicon. It's a little bit better than polycrystalline silicon, but it's really 6.5, half dozen the other. It doesn't, if I have to choose, I'm going to go with mono. Mono is a little bit more pure. It's also a little bit more expensive, but polysilicon, the cost advantage of polysilicon makes it about the same as mono. I mean, they're it's like they're Irish twins. They're that close together without being exactly the same. All the other stuff, thin film, see-through panels, all of that other stuff is just a very solar shingles. There's a very small section of the market. It's not worth your time when you're just getting into solar to worry about thin film and all that stuff. And actually, that was a much more interesting discussion 10, 11, 12 years ago when silicon was more expensive. But now that silicon that is literally what you see on a solar panel that those cells are made out of, it's like just a couple bucks a pound, at the manufacturing level. I mean, 40 pounds, 40 bucks, of silicon in a solar panel or less, it's cheap. So that's why silicon is so successful, and in fact, that's why the solar industry exists today. It's the silicon manufacturers. It's a silicon industry. Anyway, let's take a closer look at module specification sheets and see what we get. We get a power rating, how many watts of power the panel outputs. This voltage information is used by designers who are doing like pencil and paper calculations. But nowadays, most of this stuff is done through computer design software. But it's still useful to know, this is a little bit of an older panel, a little bit lower wattage. Most solar panels today are around 350 watts, and still at about 9 to 10 amps. The voltage has crept up to be about 40 volts. What I would say between voltage and amperage on a solar panel is that the voltage jumps up and down a little bit more, is more subject to temperature changing based on temperature. Whereas the amperage is a little bit more steady. So in a couple slides, we're going to talk about temperature impacts, and what we'll see is that the temperature degradation impacts voltage a lot more than it does amperage. We have this MP, and this stands for maximum power point. I wouldn't put too much stock in the maximum power point concept of a panel. This is basically the MP. The maximum power point is the operating voltage and the operating amperage, whereas the other aspect of the spec sheet is the short circuit current. If this thing is ground faulting, how much current is it going to be dumping directly into the ground under a short circuit? That's your short circuit current, and that's what all your cabling and conductors are sized around as a starting point. So, the actual operating current versus the design current is a little bit less. Similarly, open circuit voltage is like what happens when you have a battery and a flashlight, but the flashlight's not turned on and the battery's just sitting there with some energy available. The open circuit voltage is the voltage that if the array is installed but you haven't installed the inverter yet and the panels are energized and you go and click in your voltmeter, that's the under no load. The open circuit voltage is the maximum voltage that panel is going to get up to. And so that's actually going to be a little bit more than the actual operating voltages. So if you design a solar array to be around a 600 volt maximum limit, and then you go and you test it in the field, it's going to be at a lower voltage and not going to get up to that 600 volt maximum. If you designed it around the open circuit voltage, which is what you're supposed to do. Finally, we get to module efficiency. This is how much energy hits the surface of the panel versus how much energy goes out the back side of it. So that's pretty impressive, I think, that out of all the energy and sunlight, a solar panel can capture about 20% of it. And that number increases every year. I've been in the industry long enough to hear very smart professors say, solar will never get above 11% or 14%. And they always find ways to tweak the panel silicon structure to uptick that efficiency even more. So that's still climbing. And one of the most important parts to understand on a module spec sheet is that all of these voltages and wattages, and amperage is done at a standard test condition, rating. So, just like a car is going into a laboratory test to get its mile per gallon rating, solar goes into a laboratory test to get its wattage rating and its voltage rating and its amperage rating. And a solar panel at midday, when the roof is at its hottest temperature and the sun is directly overhead, that's a very different condition than solar in the winter time on an overcast day. And so the amount of power that the system produces is not going to be what's on its spec sheet. It's going to be how, the module, is at that sliver in time. And the sliver in time that a module is rated for, well, what is that? How does that compare to a normal day, or what you would think of as a normal day? Well, let's see. 1,000 watts per metered squared irradiance. So where do I go to get that data? Well, actually, there's a solar design software that's free to use called PVwatts, and it's I'm just going to pull over an example just real quick. We're not gonna explain PVwatts. We do that in other classes, but it's a very easy to use software. I'm just going to put in, right now I'm in Biloxi, Mississippi. So we're putting in our system array size. I always recommend doing a 1 kilowatt solar array because that forms a scalar. We've seen Biloxi, really good solar production. The coastlines of the US get a little bit better production than further inland because they don't have as many clouds, or the clouds kind of blow over a little better. But anyway, that's neither here nor there. You scroll down in PVwatts and you download the hourly results. And what you get is the raw data for PVwatts. And why it's relevant to today's discussion is we can get the beam irradiance, the amount of direct sunlight in the air. We get the diffuse irradiance, the amount of overcast light in the air, and that's useful for all sorts of things. But finally, we get to the plane of the array irradiance, which is based off the array tilt and the array azimuth. In this case, a 20-degree tilted array facing due south. We get to the array irradiance, and that is what in the lab was supposed to be 1,000 watts per meter squared. But here on this winter day, it only gets up to 400 watts per meter squared, or 360 watts per meter square, and that's only 30 to 40% of 1,000, and it'll only produce 30 to 40% of 1,000. So this winter condition, well, here's a sunny day in winter where we get up to 640 watts per meter squared. But let's go ahead and just to move the discussion along, scroll down this PVwatts raw data. So now we're in July. Okay, July, middle of July, that's perfectly fine. And we can see that in July in the morning, we don't get up to 1,000 watts per meter squared. In the evening, we don't get up to 1,000 watts per meter squared. Even in the middle of the day, we're not getting up to 1,000 watts per meter squared. So that's here we got this next day in July. The haze is gone, and we do get at high noon in July 1,000 watts per meter squared out of the production, the array. But it's not something that occurs every single day, and it really depends on how the panel is facing, and even when it's facing directly at the sun, it's not common to get 1,000 watts per meter squared. But that's what the module is done at. And so that's why you can't just take like a solar panel and be like, okay, it's a 1,000-watt solar panel. The sun is up for 12 hours a day, and so 1,000 times 12 gives me how many watt hours the array produces. That's not. There's shortcuts and fudge factor numbers for that. Even in the PVwatts interface, we got these. They've compressed how much sunlight is going into the 12-hour period that the sun's up, and it's saying, okay, well, we're going to compress them into 1,000-watt per metered squared hours. And so this in July, the sun might be up, the array might be producing from 8 a.m. to 7 p.m., but out of that 11-hour slice, we've gotten 6.1 1,000-watt per metered squared, sun hours out of it. So the sun hour concept was really popular back before computers, when they did solar design, to have these kind of fudge factors to say, well, how many sun hours do you get in your area? And then you could take the efficiency numbers from the spec sheet and develop a performance estimate off that. It's kind of a antiquated design practice, but still can be useful to know about. How many 1,000, and it all around is based around this like 1,000-watt per metered squared concept. Well, then there's this other part of standard test condition called the module temperature, and that's done at a 25°C module temperature. Okay, well, I don't know Celsius. I know Fahrenheit. How hot does it get up on a rooftop? Again, PVwatts can come in handy in this PVwatts hourly data, which is a free software. The government puts it out. They combine weather data. Anyway, we got this ambient temperature column, and then we got the cell temperature column, which is pretty cool because now we can relate ambient outdoor temperature to rooftop, module temperature. And the point is, this standard test condition on the module spec sheet is at 25°C. We go and we look at our PVwatts data, in the middle of the summertime. So here we are in July again, and we're looking at our temperatures, and our panel is getting up to 50°C, not 25°C. So the irradiance is not only off, but the module temperature is off as well. That air mass thing is too advanced for this class, but basically at high noon, air mass is at a 1. And so this is saying, okay, our test is done at like 10:30, 10:45, And if I wanted to see how my solar array was doing compared to its spec sheet, I might wait for the springtime, at 10:30 in the morning, on a bright sunny day with no clouds in the sky, and then go look at my production at that time, because that might approximate standard test condition. Okay, but it gets really hot on a rooftop. Can we use a spec sheet to determine what the performance will be on a hot day outside? And the answer is yes. So on a module spec sheet, they're called temperature coefficients. I guess I blocked out that last part, but this says temperature coefficients. So we got a temperature coefficient of voltage, of current, and of power. Remember, a volt times an amp is a watt. So voltage times current equals power. And so we have different temperature coefficients to say, okay, this is how voltage is adjusted for every degree Celsius we go above standard test condition. So standard test condition is done at 25°C, and we're at 50°C. We take the differential, which is 25 degrees, and we multiply it by 0.34%, and we see, okay, that's about 8 or 9. And you say, okay, well, we've lost 8 or 9% of our voltage because of I guess it should be a little, well, anyway, we've lost 8 or 9% of our voltage because of rising temperature. What we can see is the current is a positive sign and the voltage is a negative sign. And what this means is as temperature increases, voltage is going to decrease. And as temperature increases, amperage is going to increase. Memorizing that, how is voltage impacted by temperature? It's really important. It's easier to remember voltage, I think, first, and then just know that amperage is the opposite or the inverse of that. But for today's discussion, we're going to look at power. I'm going to say, okay, 0.4% minus sign means if I have a 25-degree temperature differential and I'm up at 0.4%, that means I've lost 10% of my power just because of temperature alone. And then the array irradiance is more kind of directly proportional, where if you have twice the amount of sunlight in the air, you're going to get twice the amount of power, and that's assuming the same temperature differential. And so the solar array temperature is way off, the amount of sunlight in the air is way off, and so it's very hard just to look at a module spec sheet and say, okay, I know how much energy this is going to produce a year. Inevitably, you have to go and do a computer model that calculates it for every hour of the day based off temperature, based off performance degradation. PVwatts is doing that all behind the scenes. Okay, so here, how do we look at this graph? Basically, this point of the graph is where we have all voltage and no amperage. So this is our open circuit voltage. And then on this graph, when we have no voltage, we have all amperage. So this is our short circuit current. And these little dots here are what they call the maximum power point of the module, that says that, hey, if this solar panel is operating at a little bit less current than its short circuit rating, a little bit less voltage than its open circuit voltage, we'll capture the most amount of a volt times an amp, which is a watt, by having the most area under this curve possible. That means we're getting the most power out of the curve possible. And so but what that also means is, if the module had any more open circuit voltage, it would be short circuit. There wouldn't be any load on it. It would just be at its open circuit. And if the module had any more current coming out of it, it would be short circuiting into the ground. And so, for every electrical use, you turn on the load, the voltage is going to drop a little bit. So now we got a little chart that is really not that useful, other than just to understand the concepts. When they're talking about maximum power point, they're really talking about the module operating voltage, module operating amperage under normal operating conditions. And now we see a little bit more about array irradiance and how it appears on module spec sheets. And we understand that all of these values are deriving from a rather chilly environment. A 25°C rooftop temperature is kind of like a 55° Fahrenheit day outside. And so that's not what that means is when you get into National Electric Code and you start to put in these design numbers into your design work, code is going to require additional safety factors beyond what is normal for common electrical design in order to say, look, you know, the voltage and the amperage that you're designing with on the spec sheet is way off compared to what it will do in the field. And so unless you're making engineering calculations, you're going to have to apply additional safety factors, because ultimately when you're designing with code rather than with a calculation, it's a series of safety factors to get to your safe design. So here's some other items on the spec sheet. We got the load of the physical loading data. You know, it says, you know, what our snow load rating is for, what our wind load rating is for, what our, you know, hail impact speed test is for. You know, a tolerance. And that's kind of those power tolerances used to be way larger in the past than they are today. You know, it used to be that that solar panel tolerances were plus or minus 5%. You know, now they're plus or minus 1%, sometimes minus 0 plus 1 or 2%, where they're guaranteeing no negative power tolerances. What happens is silicon is either grown on a sheet like a square, or it's grown in a cylinder like a salami, and so they're cutting, you know, the sheet, or they're slicing the salami, but I'm trying to see if I can't change the color on my pen, but I don't see that. Maybe I should use a different pen then. The short of it is the interior of the rectangle or the interior of the cylinder is more pure than the edge conditions. So it used to be they would take these slices of silicon or slices of the sheet and just throw them onto the solar panel, and it would have this big tolerance. Nowadays, they test the cells before they make the panels, and the more efficient cells go onto the more efficient panels, less efficient cells go onto the less efficient panels, and that's why you will get one spec sheet is like listed for 250 watts, 255 watts, 260 watts. It's because they're doing the cell sorting. They're making all these different wattage modules out of the same production batch. We're going to talk about warranty in a minute. And some of this other stuff, environmental ratings, little too broad in scope, but these are pretty similar throughout the industry in terms of name brand modules. What might be a little bit unique is the ability to specify the module frame thickness, which can be useful for, as they say, durability, hurricane zones. Sometimes to get this stuff, you actually have to get out of the spec sheet and go into the actual manufacturer module installation manual, and at that point you'll get more information on pressure ratings and load tolerances. So for example, here's a solar panel, and what it's saying is we're going to give you a variety of different ways that you can attach this solar panel to a rack. Installers will care deeply about this information called a clamping zone, that will tell, you know, how far up the frame or close to the edge can you put, you know, the attachment points from the array to the rack, and that influences the deflection of, you know, wind load and snow load on the module, and that will you will have to stay within those clamping zones in order to maintain your module warranty, but also you have to understand how these clamping zones impact the structure of the design. So, you know, for example, out of all these options, the strongest one is putting an additional rail behind the panels. Okay, that makes sense, giving it some more reinforcement. You know, and that would be a technique you could use in, say, Florida to meet your, you know, hurricane zone requirements. I'm actually kind of fascinated by this. Is a side note for another day, but you pick your right solar rack and you can actually plumb it and put a heat circulating roof or heat exchanger up on your rooftop. It's kind of like my next ambitious concept installation design, but done too much ambitious stuff. I need to get more into some regular stuff for my next couple projects at least. Other spec sheet items, the size of the solar cell, the number of cells, 60 cells, 72 cells, the thickness of the module frame, the weight of the panel. They will brag about the quality of their glass. Sometimes the type of plastic on the back is important, but by now in the industry, they stick to mainstream manufacturers, and there's 24 mainstream solar manufacturers still in this industry. So by and large, module quality is very good. The type of frame, the color of the frame, we'll get into that in a minute. The gauge of the wires coming out the back of the panel, notably, it's number 12. A lot of solar installers are going to upsize to number 10 or sometimes number 8 in order to reduce voltage drop. But generally, that's going to leave you with a much larger ampacity in your wire than what's necessary. The manufacturer is saying, where it's number 12 is perfectly acceptable, and it is. If the array is close to the device it's being plugged into, in particular. It's the type of connector. The connector today is basically an MC4 standard. The only thing you have to really look out for is when you're buying MC4 connectors to make sure if they're either 600 volt rated, which is common for residential, or 1,000 volt rated or larger for your utility, large commercial and utility scale projects. Some other useful module spec sheet items, how many modules come on a pallet. I will, when you're shopping for your module pricing, to get really good module pricing, you have to buy by the pallet. Just buying a couple of solar panels isn't going to do you any good. But if you can buy a pallet, then distributors will be your friend. They'll treat you with more respect, because you're making their job a lot easier too. No one wants to bust down a pallet unnecessarily. I'll go so far as to design my systems to be 1 pallet or 2 pallets so that, I can either ship the material directly to site or easily receive it and load it, in a logistical center. And this varies. Manufacturers, some have 25, some have 30, some have weird numbers like 27 or 29. It depends on the manufacturer, how many come in a pallet. You can even find the commercial equivalent, how many come in a shipping container, although there's not quite the same price drop between containers and pallets, at least in my experience. And it's pretty interesting how much detail is actually revealed in a module spec sheet. Some manufacturers will actually hollow out this piece of metal. So they'll reinforce at this point, but then very quickly go to a much thinner strip and then move it back out. Notably, the US manufacturer Solar World does this with some of their panels. And what that means is on standard solar panels, you're putting your solar racking underneath, and you'll also have the option to run the modules in landscape And so that means the modules, you know, could go in portrait orientation or landscape orientation, and the racking could go in portrait orientation or landscape orientation. And you know, many U.S. roofs have rafters going from the bottom of the roof up to the top of the roof, but on other roofing systems, such as tile rooftops or metal rooftops, you have support beams going east to west rather than north to south, and that'll impact on whether your racking goes east to west versus north to south. And some designers will just say, well, the modules are going to be whatever orientation best fits the racking. But architects may step in and say, no, we're going to go with, you know, landscape modules because it looks better on this rooftop than portrait modules. And not all solar panels being made out there are flexible. You know, back in the day, every module was so robust with a big, robust module frame that you could pretty much do whatever you wanted with it. Mount it portrait, mount it landscape, whatever. You know, nowadays, pricing is so competitive that in some ways, modules, you know, they've gotten 10 times better in terms of quality, but you know, manufacturers are looking at, you know, hey, if we can cut out this little strip of metal here, how much money are we going to save? And sometimes that means your module is not as flexible or as strong as it has been in the past. So you can pick up on whether it has a full frame or a weakened frame and what that might mean to your design if you get really good at evaluating a module spec sheet. Even the information like how much length comes off the back of the module for that MC4 connector can play a role in like super advanced solar design. So for utility scale panels, you know, the rule of thumb for the length of these things is that the cable is long enough so that it could be plugged in side to side, you know, or it could be plugged in east to west. And this is the stuff that like solar installers really like to pride themselves in or think about or agonize over, which is you end up having extra slack in your cable that then has to be tucked up nice out of the way for good workmanship and, you know, not attract the eyes of critters and rodents, things like that. So you end up with a lot of slack on these MC4 cable whips. And on 72 cell modules, which are a little bit taller than 60 cell modules, the length of that cable whip is a little bit taller as well than on 60 cell modules, so that it could be installed both in portrait and in landscape. And so what they've discovered in utility scale sites is the 72 cell modules have a long enough module width that you can actually not plug them into the next door neighbor, but you can kind of leapfrog and go into every other neighbor and then come all the way back down the line with your plugs. And so instead of having, this is called a home run connector, which is the custom cable that you're making at the end of the circuit that's going all the way back to, say, your combiner box or your string inverter. You know, this is the home run circuit. You know, in a leapfrogged or skip-stepped utility scale plant, the home run connectors start and stop at the same spot, and you don't spend the money on this much cable length, and you don't have the voltage drop and the efficiency loss associated with that much cable length. And so it's kind of an advanced utility scale ground mount installation technique. With 60 cell modules, the cables aren't long enough to do that. Maybe that's a little bit too splitting hairs or missing the forest for the trees, but you know, the point for today's program that I'm trying to make is even that level of advanced solar design with planning out your cable management, you know, can be done with a thorough spec sheet analysis or review. 3 1/3 feet by 5 1/3 feet, weigh about 40 pounds. So let's talk about the module warranty. Most solar installers will tell you solar has a 25-year warranty. But what does that mean? Some utility incentive programs will require their installation contractors to provide 5-year comprehensive warranties. In another market, the standard practice might be a 1-year comprehensive warranty, depending on your state regulations. And so when a solar installer talks about a 25-year warranty on the system, they're talking about the solar panel warranty. And even then, it's a little disingenuous. Customers want to hear 25 years. They want to hear long term. And solar is long term. So how do you accurately present that? Well, there is a 25-year warranty on almost all solar panels. And what that is a performance warranty as opposed to a product warranty. And if you think you have a 25-year product warranty and you only have a 25-year performance warranty, you might get very upset. And I might think that you don't have a reason to be upset, because it turns out that the panels that have 25-year performance warranties cost, almost twice as much as the panels that don't have the 25-year performance warranty, because you get what you pay for. And there can be very valid reasons to go with high-end modules that cost a lot of money and have long-term performance warranties. At the same time, there can be wisdom in saving that money and saying, I don't know what my exact maintenance need will be in the future. Maybe it'll be maintenance that isn't covered under the warranty. And so I will keep my money for that maintenance event. Thank you very much. And go with a cheaper solar panel whose only difference between panel A and panel B is cost and the performance warranty. Again, you get what you pay for. But what are you paying for? The performance warranty is warranting the quality of the cell on the solar module frame. That assumes that if nothing is going wrong with the solar panel itself, so the solar panel is just sitting there 25 years down the road, hasn't been touched, is just chugging away, that the cell itself will not substantially degrade or go kaput for 25 years. So they're saying the life of the panel is 25 years, and if the cells stop working before then, that's covered under the performance warranty. The product warranty is for everything else, such as the connection point between the solar frame and the solar panel itself. And so if the solar frame falls apart and water gets into the panel and it shorts out the panel, that's not a cell issue, that's a module frame issue. And to a customer, they might say it's the same issue, but really it's not, because the manufacturer can vouch for the quality of the cells, but he can't vouch for the quality of the installation. How the panel is handled from the time it leaves the factory to the time it's put on the roof, and then furthermore, how the system is designed and installed, a hurricane zone versus a non-hurricane zone, an environment that has severe temperature extremes versus one that doesn't, a saltwater environment versus a freshwater, a farming facility versus a standard rooftop, where the clamping zones, if they were properly adhered to or not. All of those things can add up to result in a system failure that doesn't have anything to do with the module cell itself. And so the manufacturer is trying to split those differences to say, I'm vouching for the quality of the panel and I'm reflecting that in my cell warranty, but I'm only going to give you a 10-year warranty on everything else about the panel. And so you have to watch out for that, because that's a common misconception, is that the solar array has a 25-year warranty. That warranty is less comprehensive than you might think at first approach. Okay, so if the module falls apart, if it is leaking and shorting out because of that leak, if you put the modules on a pergola, so the modules are going straight up in the air and you get pooling water on top of the array surfaces, all of those issues might have to do with the performance of the module, and that is typically a 10-year warranty, although top-end panels can have 25-year product warranties, and they cost a lot more too. Generally, which is better boils down to where your market is. In a very high-cost electricity market with very expensive real estate, it generally is worthwhile to go top shelf. If you are in an area where the real estate's cheap and you can just do a really large solar array, then go in with lower efficiency modules, cheaper modules. If the rooftop's very accessible and you can get on the roof and get off the roof, if it's a ground mount array where you can get on and off the array site with ease, going lower end is perfectly fine too. As far as the performance warranty goes, the actual kind of performance warranty matters less than you think. High-end manufacturers will give you a warranty that's broken out by the year. And so they're saying, I'm going to warrant my panel for 97% for the first year, and then the power degradation year over year will not exceed 0.7%. And there's very real subatomic degradation levels that go into forming these numbers. Not enough time in class to talk about them. But there's a year one degradation that is greater than the year 2 through year 25 degradation. Basically has to do with the electrons warming up to the system, or breaking into the system would be a better term. And so finally we get to year 25, and almost all the way across the board, you get an 80% power output rating at year 25. So they say, look, if you're installing the solar array under a standard job site with good workmanship, nothing weird going on with your environment or with your design, then you can expect a 25-year life out of the system, that at year 25, the panels will still be doing 80% of what they do today. And that's where the industry debate is over today, is like, what do we do at year 25 when the system has paid itself back, made the customer a return on investment? Will the system start looking obsolete or not? And you got two different answers. You got, well, no, it's still producing electricity. You can leave that system on the roof for the next 40 years and it will still work for 40 years. As long as it's swimming along at year 25, it'll be swimming along at year 40. On the other hand, the other line of thinking is, yes, but solar 25 years from now is going to look very different than today, and so it might be worthwhile just to repurpose the array, at some point before the end of its actual life. And there's policy and insurance and loan financing issues that go into the life of a solar panel. The general trend is to argue for even longer life than 25 years. We've been modeling solar having a 25-year life for the last 10 years, so it's not anything new. So manufacturer warranties can either give you that 97% year one and then a 0.7% year over year degradation, and the actual performance loss is maybe 2%, 2 to 3% in the first year, and then about 0.5% for the rest of the time. And so you can get warranties that very closely follow and track with the actual degradation of the module. A little bit lower end warranty is, say, okay, well, we'll give you a 90% warranty for the first 10 years, and then we'll give you an 80% warranty for the next 15 years, a literal stair-step warranty rather than a year-over-year warranty. You know, I actually think the stair-step warranty is a perfectly fine warranty, and if it costs less money, you know, in the right market, I would be tempted to go for it just because it costs less money. And the reason for that is how modules actually fail. When they do fail, what goes wrong? So when you're actually triggering this warranty, what does your typical conversation look like? And what happens when a solar panel fails is, for whatever reason, somewhere in the panel there's a defect. Okay, so maybe it's a little soldered connection point that, you know, blew apart with thermal expansion and electricity, and, you know, maybe some water got into the panel and it got between the cell and the surface of the module, and the voltage vaporized the module and it left behind some particulate, and that led to some corrosion and it corroded the solder point. We could come up with a lot of theoretical reasons. There's something wrong at that point of the module. What's going to happen is your solar pump modules have bypass diodes in them, and this is for rather puny, because often shade is more complicated than this, but it's like, okay, if this section of the solar array got shaded, then the module power output would only drop by 2/3. And it's puny because, well, if this module drops by 2/3 on a traditional array, all the other modules in that circuit will drop by 2/3, and the voltage will start flickering, and the inverter will get confused anyway. And how often does a shadow just fall on, you know, that portion of the module and not the rest of the solar panel anyway? And so it's really not, you know, terribly effective. But in terms of if there's something wrong with the panel, you know, if something's not connecting, that panel is going to be producing 2/3 exactly compared to what its healthy neighbors are doing. And so if I'm looking at solar monitoring and I'm seeing something's wrong with the panel, you know, I'm looking at it, and almost always the voltage is 80%, exactly 80% of what its neighbors are doing, or exactly 2/3 of what its neighbors are doing, or exactly 1/2 of what its neighbors are doing. And so it's like, okay, well, it's a problem isolated to these bypass circuits. And so that's always beyond the 90% stair-step warranty or the 80% stair-step warranty. When something goes wrong with a panel, it's obvious, and it's obviously going to trigger the warranty. It's not this like, oh, is this 97% with a 0.5% a year better than this other warranty, you know, issue. You know, what triggers a warranty issue is you're looking at your array and one panel is not doing as well as the others. And sometimes that comes in during shipping. And so, you know, good installers are going to be checking their module, at least circuit voltages, you know, on the install to make sure that everything's correct before they wrap up on site and call it a day. And so I wouldn't be as worried or obsessed over module warranties as you might. In fact, at commercial projects, you can even buy warranty insurance, where a third party will pick up the warranty of the project if you don't trust that the manufacturer is going to have good balance sheets. But, you know, really, when it comes down to it, as an individual project, the warranty is as good as your supply chain. You know, if you're buying from a reputable vendor at a decent markup, you're going to be you should expect better customer service than if you're going after, you know, bare knuckle supply chain management where you're reaping the rewards of cheaper product. You know, you're buying one panel, and if that panel is not producing slightly what it should be, you know, you still have to go through the horrible process of proving to the manufacturer that it is a warranted issue, and that manufacturer might come back with a series of tests that they want you to perform to prove it. And, you know, if you're just an individual do-it-yourselfer, it might just not be worth the hassle for one solar panel when it comes down to it. You know, what's more important is to not have that false impression of strength when you unpack the solar panels and are putting them on the roof, and instead treat them with respect. Because the biggest thing is not when you smash a solar panel pallet with a forklift and bash some panels up, or when the delivery driver is going too fast around a curve and the pallet slides and bashes something. You know, that's what's common. You're always looking at your deliveries to make sure they weren't banged up. You know, modules will fail by leaning them up against the wall, and the wind blows them over, and they smack on the ground, and they crack open all the module glass. You know, what is more insidious over the long-term life of the project is if the installation was not installed well, but not in a way that damaged the panel up front. So what I mean by this is you can cause little micro cracks within the solar panel itself that are not obvious and that are not immediately going to cause a problem, but the electricity flowing through the panel over its life will make those micro cracks into larger canyons, almost like water carving out the Grand Canyon. Little defects in the cells can start to unzip, and you get lines and streaks going across your module cells, and sometimes that creates problems, sometimes it doesn't. There's a degree of inevitability in module failure. The best thing you can do is not put heavy objects on the module surface itself. Don't put your elbows, don't kneel on them, don't lean on them. You know, if you're having to Spider-Man across a solar array, then put that module frame to use, and use the module frame to put your hand on or your arm on to get better grip with your installation tools. But, you know, what's common is you get the modules on site, and then people want to stack, you know, tools and boxes and toolboxes on top of the module pallets before they're installed. And it's, no, you know, that middle section of that module, of that array there, is not intended to have, you know, a 200-pound, you know, elbow point load pressure on it. You know, it can take a glancing blow of 1-inch hail at 40 miles an hour, but it can't be stressed and cracked down, you know, 1 inch because some person's kind of putting their whole body weight at a particular point. So you don't see that in the spec sheet. That's going to be more in the module installation manual. We're going to take a break in just a minute. I want to close out the solar module discussion with just a variety of different kinds of solar modules. You know, my favorite is to specify an all black panel. That'll give you a black frame and a black back sheet. And the answer is it just looks better on the rooftop. So for residential systems, I am always specifying all black panels. It just looks better. And there's low-end all-black panels, which I get all the time, which still have their grid lines on the top. You know, on top shelf all-black panels like SunPower, these grid lines completely vanish, and it looks more like uniform glass. In my experience, all you need to do is get, you know, 100 feet away from the house, and you can't really see these grid lines anymore. There are solar shingles on the market, but I don't know any installers who prefer them and I really don't know any installers who install them either. You know, I've seen them, but they're too expensive. They're not as good as regular solar panels, and they're a lot more work to install. Effectively, you're installing a bunch of small solar panels instead of larger panels, so that jacks up the labor cost. And they're not as good a quality either. So I don't know. I don't think they look any better than an all black solar array, provided, you know, it's the array layout that's more important, really. Frameless solar panels are pretty interesting. They don't have a metal frame on them, and that makes them easier to break. But it also could make them cheaper. Back in the before the solar import tariff, I was really interested in frameless modules that have plastic back sheets, because it's really just the lightest weight, cheapest solar panel you could make. But most frameless solar panels have a glass front and a glass back. And the reason why you might want a glass front and a glass back is not like in this case where the customer is just showing off having a thinner framed solar panel. But if you're in an agriculture facility where there's a lot of ammonia gas, or maybe on the coastline if you're afraid about saltwater spray, going with an all glass panel can have some corrosion benefits, insulative benefits. It's very rare though. One module that you can find nowadays, they're pretty common and not that much more expensive, is it's called a bifacial module, and they can be frameless or they could also not be frameless, but a bifacial module has glass on the front and glass instead of plastic on the underside so that you can see through them. You know, they're marketed as, oh, you can capture sunlight on the underside of the array as well as on top. And I'd say that idea is not proven out yet. If you are going to capture light on the underside of it, it needs to be up in the air, not right on the roof line. You know, and furthermore, shaded light conditions, PVwatts will tell us that, you know, on a shaded day, you're only going to be producing, you know, on a very shaded day, you know, 10% of what you would be doing on a sunny day. And so you can only pick up 10% more light. And if the solar array is only 20% efficient, you know, that's a 2% increase in production. So the real question with bifacial modules is that the cost difference between a piece of plastic underneath the module versus a more expensive piece of glass worth the extra 2% in production value? You know, that's a discussion being played out at the utility scale market as we speak. But I think another reason to get bifacial panels is architectural, and that's another thing where we need more building engineers leading the charge, because solar installers are not interested in making these kinds of showpieces. They don't know enough about the building envelope, water tightness, waterproofing. Is they keep it simple. You know, cheap, cost-effective solar is just on top of a roof, not part of the roof. But if you want to make solar part of the roof, this is a good one to select. So to kind of finish out our module discussion, where do I go to buy solar panels? What I do is just shop around. You know, I'm buying by the pallet. That makes the logistics easier. I'm going on to multiple online vendor websites, so multiple chains, supply chains. I try and find newsletters to sign up for, because they're not checking, you know, they might have a dealer program or an installer program, and you might not be a licensed contractor, you know, that would normally be what qualifies to buy at the contractor pricing, but you want the contractor pricing because it's cheaper. So how you get that contractor pricing is present yourself professionally. You know what the price that they're charging their contractors by sneaking onto their newsletters. And then when you're ready to do a project, get their pricing that's in the newsletter, and you see what panel they're buying, and you go and you look up at how many panels are in that pallet. You design a system based off that pallet, and you call them and say, hey, I'm a first-time buyer, but I want to buy this, this, and that, and you know, I don't know if I qualify for your contractor price, but you know, I'm on your newsletter, and I'm an engineer, and this is my first solar design. You know, that the supply chain in the solar industry is a lot softer than in other trades like air conditioning. And so my experience has been, as an engineer, I have been able to convince suppliers who do not have, who have, a little bit of a barrier to purchasing, to sell to me based on the fact that I'm an engineer with a solar design in hand, ready to make a purchase of the products that they're carrying. So I do think that you, as a lay person in the solar industry, can buy solar panels for the same pricing or near the same pricing that I do as an installer, just by rolling up your sleeves and doing some supply chain management. And usually that also means doing a little bit of the design work on your own. With inverters, I guess the understanding the jargon is gonna really help you. We talked about earlier that solar cell or a solar panel is actually referred to as a solar module. A series of modules on a circuit is called a string. This is just kind of a jargon term, but a DC circuit is referred to as a string. And so when you have a bunch of modules all plugged into each other, positive, negative, positive, negative, positive, negative, that's one string of modules. And if there's another circuit of modules wired right next to it, that's another string of modules. And so a multiple circuit solar array would have multiple strings of DC circuits. So I mentioned that because the standard kind of inverter is a string inverter. And so you take, all the circuits of the panels, and, it used to be that we would take all the circuits and put them into a box and then wire them together into the inverter. Nowadays, we generally eliminate that combiner box and just have the circuits go all the way back to the inverter itself. And so this inverter that is accepting an entire circuit, or 2 or 3 or 4 or 20 of solar panels, that's called a string inverter. And at the commercial level, these things get large enough to differentiate between a small string inverter and a large string inverter. Commercial inverters are called central inverters, but a central inverter is a central inverter that can have multiple strings or circuits, plugged into it. Well, these string inverters is like the first kind of inverter system. The other kinds of inverter systems are of a group called module level panel electronics, abbreviated as MLPE. So module level panel electronics. Module level panel electronics take there's 2 major forms. The first is microinverters, and basically instead of having a string inverter down on the ground that all the panels plug into, instead you have multiple inverters, in this case 1 per panel, and every panel gets their own inverter, and that means you're at AC electricity instead of DC electricity. You're having AC right out the panel at the rooftop. So microinverters are very popular especially for new to solar installers, because it gets you right at home in that AC electricity. So like if you want to convince a regular electrician to do a solar array, having it be a microinverter array is a great idea. Now, the problem with microinverters is that it is more expensive to buy a whole bunch of inverters instead of one inverter. And so the other kind of module level panel electronics is a compromise solution where they say, hey, we're only going to take half of these microinverters. We're only going to take half of the stuff that's inside each one and put that up on the rooftop, but we're still going to have one inverter for the entire array down on the ground. And so instead of doing, DC to AC up on the rooftop, now the boxes just do DC to DC. They do a little bit of DC current control and current regulation, but it's a little bit cheaper than the microinverter solution because you still have some economies of scale of having just one inverter for the whole system, although you still are buying and wiring all these little boxes. But the wiring part, you just have to make sure that there's more connectors, so you have to make sure all the connectors are snapped in correctly. But to a professional installer who knows what they're doing, it's not an inordinate amount of additional wiring. It just has to be correct. And but even so, this is not as cheap as doing one string inverter. So why do we do module level panel electronics instead of string inverters? Well, you don't in all cases. At the utility scale on the ground, they do string inverters or central inverters because it's the cheapest. The reason that microinverters and DC optimizers were invented is different than the reason that we use them today. It used to be that sunlight is good for solar and shade was like the Black Plague. Shade was the COVID-19 of solar design. You get a little bit of shade on your whole array, and it starts having impacts throughout the entire system. So what would happen is a little bit of shade would shade one panel, and it would either turn off the panel entirely, or it would cause the panel to drop by 1/3 or 2/3, and that would also put a kink in that entire circuit, and so the entire circuit would drop down to 1/3 or 2/3 or nothing at all until the shadow would move. And so a little bit of shade would impact that whole circuit, but the problem is when you have multiple circuits going into the one string inverter, and now some of the circuits are turning off and other circuits are turning on, the string inverter gets confused and says, look, voltage is jumping all around, I'm turning off until this is settled. And so clouds passing over the arrays would turn the arrays off beyond just the impact of the shade on the circuit or on the string. And so in phase, they make microinverters, said, we're going to invent a shade tolerant system. Now, that doesn't mean that the panels produce more electricity in the shade. You should not have a shaded solar array. It does not work in the shade, or if it does, it works substantially less than shaded. But there are shadows that are either unavoidable or temporary. So a chimney, it might just shade one or two panels near the chimney and that's it. But if that has ramifications on the rest of the system, then you cannot go anywhere near the chimney. There might be a portion of the roof that is sunny for 11 and a half months out of the year, but for 2 weeks in December, it's shaded by the tree line. And it might be a good decision to install there anyway. I think that you can talk yourself into a situation that your client's not going to be happy with pretty easily. You can say, okay, well, you only have a limited amount of roof surface for a solar array, and there's only so much sunlight that can fall on that roof, and you have shade issues, and you can either cut down the trees or not, and so we're just going to fill up the roof with solar, and you can cut down the trees or not, but we're going to use microinverters to be shade tolerant. And while that is perfectly good line of thought, of the customer, they get the install, they get really happy about having solar, and then they start to see that their system is only online for 2/3 or 75% of the time because of the shadows on it, the other 25% of the time, and they don't like that. Customers want to see their systems working 100% of the time. So there can be a rhyme and a reason to put solar in a partially shaded area, but the best thing to do in that circumstance is be very upfront with your customer about why you're doing that, because they'll be able to see, now that you have a box behind every single solar panel, you have a monitoring system behind every single solar panel. So what the microinverters or the DC optimizers do is they enable one module to be shaded and the rest of the system to remain healthy. They allow something to go wrong with one module out of the whole rooftop without taking the entire system down. And that's good, because what fails is the microinverter itself or that power optimizer on the roof itself. Now that you're putting all of these boxes up on the rooftop, you're inserting, a lot more failure points in a place that is dangerous to work on, which is the roof. And so this was a controversial issue as to whether or not you should use microinverters, because while they do have some benefit for shaded rooftops, the question is, should you always use them? Are they so much better that they're worthwhile to use all the time despite the increased cost? And National Electric Code has effectively said, yes, we want you to use microinverters or a DC optimizer system, which still has the control boxes behind every single panel on the rooftop. That National Electric Code has pretty much said you got to put these controllers behind every single every single panel on the rooftop gets a control box behind it, because of fire safety. Basically what code says is you have to have a way of turning the solar array off, but there's no off switch to the sun. And the idea that you could have a tarp that covers the entire solar array, that's not cost effective either, or pragmatic. It used to be that these rapid shutdown boundaries were much more flexible than they are today. And so it used to be that the boundary was, within 8 feet of the array, you had to have the array shut down. Now they're regulating the actual wires inside the array boundary have to reduce from a high voltage to voltage that's under like 90 volts within a minute of pressing a button. And the only way to do that is to put the controls behind each individual panel, or at the very worst, every other panel has a control box now. And so if you are installing on a rooftop and intending to be compliant with NEC 2017 or NEC 2020 for roof mount projects, you have to use microinverters or DC optimizers. And it's a pretty good idea anyway, because they are from an electrical fault standpoint, an electrical safety standpoint, more can go wrong when you have this high voltage circuit from the solar array back to the string inverter that's an uncontrolled circuit. More can go wrong than if you put, you know, a safety device box in between to monitor it and to turn that circuit off when you press a button down at the side of the building. You know, the downside to microinverters and DC optimizers is they cost more money. This is one of the reasons that solar costs more in the United States than it does in other countries, is we have this rapid shutdown mandate. But this rapid shutdown mandate's been on the books for a while. I believe it started in 2014. It might have started in 2011 and gotten stricter in 2014. Yeah, I think that was it. And it's gotten even more strict in 2017 and even more defined and strict in 2020 in terms of, you know, do we define the boundary to be outside the array or also inside the array? And over time, what we've seen in the U.S. market share is that SolarEdge and Enphase, even though they were not the initial brand names in solar inverter technology, at least within the United States, they have become kind of the industry standards for rooftop solar because of, you know, SolarEdge pioneered the DC optimizer and Enphase pioneered the microinverter. And you know, ABB and SMA, you know, they have their own devices or partnerships, but pretty much rooftop solar has boiled down to needing a DC optimizer or a microinverter. So which out of the two do you select? You know, so it might be that you can still use a string inverter and find some third-party boxes to put in line rather than an integrated system, and maybe that'll save you some money or maybe it won't. You know, generally speaking, when I'm doing string inverters now, they're not on the rooftop, they're down on the ground, at which point they're a great option. If you have an unshaded solar ground mount, string inverters absolutely are the way to go because they're just as good, if not better, and cheaper. You know, out of DC optimizers versus AC microinverters, the microinverters are more expensive. The optimizers are a little bit more difficult. I'd say not that much more difficult, but they are a little more difficult. You know, so solar installers prefer DC optimizers. SolarEdge does more business than Enphase because it's the same value with a little bit more installation difficulty at a little bit lower price. So, you know, and that's not because of quality of components or anything like that. It's just that as far as a technical platform goes, a DC optimizer platform will be inherently a little bit cheaper than a full microinverter platform. Now, microinverters are a little bit more expensive, but they are very popular, and that's because they're electrician friendly, they're hobbyist friendly, and also they scale down very well. So if you only want to do a 4, 5, 6 panel system, or even you know, anything less than a pallet, you know, anything less than 24 panels, really, microinverters are a good one. In fact, you know, if you want to design a system with a microinverter, since we're on the topic, let's look at these microinverter spec sheets. You know, it's an AC circuit, and so on the microinverter spec sheet, it's just saying, okay, well, this microinverter is compatible with 60 cell modules. You know, this 72 microinverter, higher wattage microinverter is compatible with 72 cell modules. instead of 60 cell. You know, as far as the output data goes, we have this handy number. It says maximum units per 20 amp branch circuit. So it's saying, okay, these microinverter units, they're wired to 240 volt double pole branch circuits off your service panel, and you can put 16 microinverters per branch circuit. And so if I'm designing a system and it turns out to be 16 solar panels or less, I'm just throwing that onto a 20 amp branch circuit, and that's my, you know, I'm going with microinverters. You know, and these larger 72 cell microinverters, they have more power. Lo and behold, you have to fit fewer of them on a 20 amp branch circuit. So at any rate, very easy to design with. You can have 5 on a circuit, you can have 7 on a circuit, you can have all the way up to 16 on a circuit. Very efficient, you know, environmentally rated. You know, NEMA 6, that's kind of the industry leading. You know, on a string inverter, you know, you don't get the how many modules on a spec sheet, you know, on a branch circuit. You know, on a string inverter, you have to know a little bit more about solar design. You know, so looking at this spec sheet, you know, we can see that for this particular inverter, I just kind of pulled this one randomly offline, but it looks like it's a 10 to 24 kilowatt inverter. Okay, so now we got 10 kilowatt, a 12 kilowatt inverters. It's telling us I don't know how many input circuits we have. So we have a MPPT1 and an MPPT2 circuit. You know, just like modules have their own maximum power point for voltage and amperage, the inverter has its own maximum power point for voltage and amperage. And you know, if your inverters have 2 maximum power points, what that means is they can handle 2 different inputs independently of each other. They can have an east-facing array and a west-facing array. They could have a shaded array and an unshaded array and manage those 2 sections independently. So string inverters have, in their own right, gotten more shade tolerant. Back in the day, you did not have inverters with multiple power point tracking. We also have a voltage range. You know, so this says, you know, we're operating optimally between 300 volts and 500 volts, although it's a 600 volt rated inverter, and it'll turn on as soon as the array reaches 200 volts. You know, in one of my kind of dream stretch projects, you know, we posit, well, what would happen if you wired up batteries to the solar input of a solar inverter? And the answer is, well, you'd have to have a, you know, 300 volt to 500 volt battery bank in order to do so, at which point it would turn on and start draining the, you know, converting the battery voltage. You know, anything else that's interesting about this stuff? Output power. So I guess what I'm trying to say is, in string inverter design, you would have to go and look at your voltages of your solar panels and then say how many panels are on a circuit and multiply that by your short circuit voltage. And then you might have to go look at the temperature coefficient of voltage and the minimum temperature and maximum temperature of the array, and make sure that you stay within the operating parameters of the string inverter. And that's what string sizing software does behind the scenes, which we talk about in other design classes. But the short of it is, manufacturers want to make it as easy as possible for you to design a system using their products, and so they put sizing software right on their websites for you to use. And getting back into the presentation here. And so microinverters, you go to the microinverter website, you can put in the spec sheet data, and it'll just tell you whether or not it's compatible with that microinverter, or it hints it right on the spec sheet. But hey, I've seen cases where someone's trying to build an array out of used solar panels, and they bought some really small 72 cell panels, and they were trying to use 60 cell microinverters on it. It's like, no, you know, those extra, you know, cells wired in series are increasing the voltage of the module beyond the spec of the microinverter, and so it'll pop the microinverter if the microinverter does indeed turn on and operate. So that's the main thing, is making sure you're using 60 cell or 72 cell if you're selecting microinverters, at which point there's, you know, you can implement a small system on a residential project pretty easily off a 20 amp branch circuit. So let's talk about some racking components. Mainly, we got positive attachments that lag screw directly into the rafter in most cases. And in most cases, you're buying a racking system to fit your roof, whether it be, you know, tile hooks for Spanish tile. Nowadays, what's more common is to have a racking system that provides a full tile replacement rather than trying to snake up and through. But once you've defined your attachment point, you know, then it's just you have rail that runs along the roof, and you have clips that intercept the module frame and bolt it onto the rail underneath. And so here we have, you know, our positive attachment point. This is called an L foot because it looks like an L. And these are just clips that the bottom of the clip, this bolt head, goes into the side channel, and then the top gets screwed down, and it clamps the module frame between the rail and the clip. And so in terms of industry jargon, we got end clips, which go on the very end of the array, and we got mid clips that go between two modules, and this little notch becomes a spacer in between the two. And there's some fine elements of racking design. I prefer racking systems that have a wide U channel facing the top, because I like to take my cables and lay them into the rail. Other installers don't like that because they're concerned about water filling up in this U channel. But I do this, I drill holes into my rail to have any water drain out of it. I like this because of the physical protection from squirrels and critters and debris. I feel it's a safer design. Other installers, they'll just run their cables outside of conduit or outside of a raceway, although technically this isn't a raceway, but at any rate, they'll use, you know, tie wraps or cable clips to strap the wires alongside the rail. Now here's a DC optimizer being mounted to the rail. You install them before you put the panels overhead. And there's cable management clips, two different real kinds, for traditional zip ties, but then you can also buy metal module solar panel cable clips. And it's worthwhile having bags of these things on site because these actually accomplish two different goals. You know, a zip tie is more permanently secure. A cable clip, you can kind of, pre-install and then press the cables into. So a cable clip is a little bit more flexible, a little bit easier to install than a zip tie, although zip ties have their place on the job site as well. My installs were always using both zip ties and cable clips. Generally, the overall goal is to have your cable management be so good that you can just look underneath the solar array and not, all of your cable is just nice and tightly managed alongside, kind of vanishing from sight underneath. Two other material items to be aware of, snow guards, which are little clips that you can line the array with, that essentially the function of this is to make sure that the snow does not avalanche off of the array all at the same time. So you put little, you put friction onto the array surface to prevent it from doing that. That's only used in areas of very heavy snowfall. And then you have, they're called array skirts that line the solar array and prevent squirrels and debris and pigeons from getting into them. Not all solar installers install array skirts, and I'd say most don't, but I highly recommend array skirts in areas where you get leaves on the rooftop. So even if you don't think that there's a pigeon problem, even if you don't think there's a squirrel problem because of trees being too far away, there are installers who say, no, it's worth the extra step and quality to buy this stuff and put it on. And then there's other installers who say, no, it's not worth it because it only was, squirrels and pigeons and that only applies to a very small percentage of the rooftop. So it kind of depends on if you're going over bottom dollar or having, a higher end, less worry-free or more worry-free system as to whether or not you install an array skirt. Basically where, I don't install them unless there's a tree line nearby. But I've regretted not installing them when there has been a tree line by and the homeowner says, hey, there's leaves getting underneath the solar array. That's when I start to get nervous about the solar array. So just as a debris guard, they can be worthwhile. If you're in an area where you have wildfires, that might be worthwhile. So in our design class, we talk about the standard layout being, as such for flashing and distributed points. The standard solar attachment point is to find the rafters and drill a lag screw through it, maybe use some sealant for missed holes. What the flashing does is it allows you to miss. If you think the rafters, right here and you drill your hole, that flashing covers the mistake. If you don't have a flashed system, then you have to be incredibly precise on your attachment locations. So generally, the best practice is to have a flashed system, although there are some non-flashed systems that require more installation expertise. Okay, so we talked about how modules, if you're doing something funky, like if you're running your rail east to west, but your modules are also running kind of east to west rather than in portrait orientation, you have to make sure that your racking lines up on your module frames. There are products for metal rooftops, clips, seams, penetrations, attachment points, and in fact, not just for standing seam, but there's products for screwing into the metal on a traditional metal rooftop. And I actually like these products better because a clip just clips to the top of that metal surface, whereas a positive penetration goes all the way through into the rafter or the purlin. This is a product for elevating conduit up off of the roof surface of a standing seam metal rooftop. So the industry's come a long way in terms of product selection. This is an alternate design called a railless racking system. And so it's popular when you want to do a landscape orientation, but you have rafters running up the rooftop, and so your rail would go east to west, and then the east to west rail with the portrait landscape oriented modules creates a situation where your rail does not line up with the module frame on where it needs to go. You know, one solution is to get rid of the rail entirely and just land the module frame directly onto the positive attachment points. And so Roof Tech is a company that has made positive attachment points, and they have a big, wide propylene butyl footing. You know, and the only issue with these, the main issue with these is you just have to be very precise and make sure that you're landing on the rafters without near misses. Now, Roof Tech has solved the problem by designing their system not to need to go into the rafters, but to have enough pull strength to stick onto the roof to begin with. Like, well, how do you know that that's true or that's the case? Well, you go to the racking manufacturer websites, like this is one for a very popular metal roofing system, and they'll tell you things like, hey, for our particular mounting bracket with a safety factor of 3 involved, here's our allowable pull strengths. And what we can see is if you just go into the decking, we have a pull strength of 180 pounds. If you go into the rafter, we have a pull strength of 630 pounds. And, you know, that has to do with the size of the lag screw and how many fasteners you use, how deep into the rafter you go. But ultimately, this is just a little bit more of a close-up, but ultimately, if you go through the racking design software process, you will get force load diagrams that will tell you how much force. This comes from the racking manufacturer after you input your system design into their sizing software. They're telling you, oh, the uplift force if you're staying in the interior of the rooftop is 100 pounds, whereas if you're at the edge of the rooftop at the corner, that same array would have a 300-pound uplift force. So getting back into our decking versus rafter design, we can see if we go into the decking, we have a 180-pound uplift force with a safety factor of 3. And so if you go all the way to the edge of the roof, you might exceed that threshold. If you stay in the interior of the roof, you're fine. And so the problem with like railless racking is you have to make sure that you don't go all the way to the edge of the rooftop if you're hitting the decking and not the rafters. It's a little bit less of a strong system. So we're really kind of getting towards the end of our time here, and I want to, you know, stay on time and wrap things up. But there are a couple more pieces of material I want to point out. The first is that you have commercial racking that covers the roof in concrete, and then you have commercial racking that positively attaches to the rooftop. And I'm much more of a fan of commercial racking that gets rid of the concrete, that doesn't use these trays for concrete, because covering the entire rooftop of a commercial building with loose concrete blocks does not seem like a long-term strategy. You know, the building is not assumed to have loose concrete blocks on its roof, and maybe not all the design factors that went into the building's maximum allowable load consider the fact that in an earthquake, you know, the vertical forces of this loose concrete has not been properly estimated. And so these kind of concrete systems can weigh as much as 10 pounds a square foot in certain spots. And if you get rid of the concrete and positively attach, these types of systems can weigh, 3 pounds a square foot. So don't be afraid of poking a hole in a commercial rooftop. This is a shared rail system. If you want a copy of the slide, just send me an email. I put it into the chat, so you should have it. It's johncromer@community.solar. There's just some other product selection. You can have non-metal racking. If you combine non-metal racking with a frameless solar module, all of a sudden you have a solar array with no metal on the rooftop, or in a landfill or on a floating structure. There's racking systems that are designed for above the ground concrete pours. So if you're on top of a landfill or rocky terrain, you can still have a ground mount solar project. Tracking, in the interest of time, I would say tracking is a utility scale game. This is coming from someone who's built a single axis residential tracker of my own design. It's not that tracking at the residential level is not a noble pursuit. There's just no good product out there for it. As far as ground mount goes, and I am trying to wrap this up in the next minute or two, so just bear with me, please. But as far as ground mount goes, the main things to know are that if you're in rocky terrain and you want to avoid concrete, you use something called a ground screw. A souped up bobcat can install it. If you're in clay or sandy soil and you want to avoid concrete, you can use not a ground screw, but it's called a helical post, and it does the same thing. Both of these things do not save any money compared to concrete. The only thing that they save is the logistical side of getting concrete out the site. If it's not the right site for a concrete delivery, using ground screws is a good strategy. As far as ground mounts go, residential type systems are generally installed on 2 posts instead of 1 post. And what that does is it reduces the amount of depth that the post needs to go into the ground. Single post systems, like you get at the utility scale, go 7 feet or more into the ground. And so that's just not beyond the capabilities of most equipment that you are going to just go rent for a small residential project. That said, there's always exceptions, but that's generally speaking, you go with 2 posts for residential versus 1 post for utility scale. I like the 1 post design better because it's easier to do maintenance for earth maintenance, weed whacking and stuff underneath the array with a 1 post design. But most residential ground mount systems, it's the depth of the foundation of these single posts that's going to drive you into more of a scaffold style racking system. At which points there's different ways to level it on uneven terrain. I use laser finders, but a string works pretty well too with a bandsaw. Well, let's leave some closing notes. We talk about internal conduit runs and stuff for in design classes, but for this home run circuit, for the circuit between the array and the inverter down below, I'll generally run it through the attic rather than on the rooftop. And solar circuitry, unless you're using microinverters, which is AC, but the DC circuits inside of buildings need to be in metal. So a lot of installers will just stay outside the building and wrap their conduit around. What I'll do instead is I'll specify metal clad cable for my cable run inside the house. and that'll give me that inside of metal qualification, but it's also flexible enough to run through an attic, and it's very easy to install. It's expensive, but it's easy. Another specialty component you need to buy is a transition box for going between the attic and the rooftop. So this is called a Solodeck, and often I will just buy an empty shell Solodeck and just dump my solar cable into my MC cable and keep on going at this point. You know, the problem is if you don't buy the specialty box, the Home Depot balance of system equipment material, it can stick too far up off of the roof deck to hide underneath the array. So if you want a good aesthetic, you gotta hide it underneath the array. Well, we're kind of out of time. You know, if we had more time, I would talk about MC4 connectors, which are common failure points in the system when you're making up these home runs. So you have to do a very careful job and good intentional job for, you know, when you're making these connectors, making sure the crimp is good, making sure the connectors are made up tight. Because these are common failure points in systems that don't have good connections and don't implement good cable management. You know, stuff that an electrician does over his normal course of business, not something a do-it-yourselfer would have as much respect for. You know, lastly, with interconnection, there's one thing that I want to mention, which is standard solar design. You're either intercepting the conductors between the meter and the main breaker, or you're landing the solar array down at the bottom of the bus bar. There's one other piece of material that is currently not part of solar design that I think will become increasingly popular in designs in the future, which is to also reserve the top of the bus bar for an emergency power supply. And so what I'm saying is there's a couple of different ways to interconnect an array, whether it's going into the supply side between the meter and the main breaker, or the solar side between the load side and the bottom of the bus bar. Talk about these in our design classes, and when to use a supply side connection and when to use a load side connection. But the actuality of not just having a solar array connected to the grid, but instead having a solar array connected to a battery that's also connected to the grid, but can also supply the building during a power outage, that's much more complicated. We're used to seeing our one-line diagrams being very simple. You know, what I'm picturing here is this is where the actual cables get interconnected to the grid. This is called a tap connector. These are piercing insulated tap connectors. These are standard tap connectors. But basically, this piece does this thing here. It makes the connection point. So you got, you know, wires from the grid coming in one side. You got wires from the solar array coming in the other side, and you got wires going out to the electric service panel. You know, they're all tapped together at this point. But, you know, it's one thing to say, oh, these wires are all tapped together into the grid, and another thing to say we're also adding a battery and doing backup loads. Basically, if your hand is reaching out and grabbing a hold of the electric grid, it has to let go of the handshake in order for you to power backup devices. So here's like a simplified diagram, and it shows a battery inverter connected to the grid, and then it also shows this kind of weird, and it references a critical load panel. You know, how that actually plays out is you have to have a disconnect between the grid and your battery system, and maybe some automatic transfer switches and some relays and some transformers, you know, a lot more interconnection gear in order to isolate the system from the grid if it's grid tied. And so basically, to run a house off grid when it's a grid tied system, not just do you have to have a battery as well, but you have to have this complicated interconnection equipment in order to say, okay, well, maybe we'll have part of our service panel grid tied, and then we'll have a separate service panel that's isolated. And so we'll have a transfer switch, and then the grid side component will go down and the protected side will go up. But all of this stuff costs a lot of money. Rewiring an electric service panel can be 10% of the budget of a solar array, and you're not getting anything but just relocating circuits from one side to another. That said, having a transfer switch for the entire house is very expensive too. And so one component that I think is going to be increasingly popular is to put a manual switch, because this is like $50 compared to a whole house 200 amp automatic transfer switch, which is $700 or $800. And so what this breaker does is it forces the only way to open this breaker is to close the main. And so this is like for a generator that would provide temporary power during a blackout. And so what you can do is, instead of protecting a critical load with your battery inverter, is you can wire your critical load panel up to the generator interlock switch and power your whole house during a blackout with your system, rather than just the critical load panel. Now, there's a lot more assumptions in there that you have to make. You have to have a battery. You have to make sure that the inverter is not backfeeding itself, which will just waste a bunch of energy, if not burn the inverter up. So you might have to, have another breaker that turns off. You gotta, this is kind of advancing solar design. But what I would think about in terms of material selection is, when you get to your service panel and you say, okay, well, my solar array is going down at the bottom of the bus bar, you might also want to reserve the top 2 breaker slots on your service panel for future system expansion, because no bones about it, solar customers want backup power during a blackout, and this is something that's still being established.